Hey folks, so our last video of new material for this unit is about escape velocity, and in my estimation, the College Board just kind of used orbital motion as an excuse to fit this in. I don't believe it to have a very specific link to rotation, although in theory it could. I would associate this more with just a rocket launch. Escape velocity is describing how to escape the gravity of a planet. So the minimum speed an object must have in order to escape the gravitational pull of a planet. So it is a solution to a conservation of energy problem. We talked about this in the last video. Kinetic energy of an object, 1/2 mv squared. Gravitational potential energy, this time between a planet and a rocket, let's say, is negative g big M little m over r. And then mechanical energy is always kinetic plus potential. And so our theory here is that in order to escape gravity, you have to have obtained the maximum amount of gravitational potential energy, which is 0. And if we are looking for the minimum speed necessary, then we are also going to need to have used up all of our kinetic energy. So another way to read escape velocity is what is the speed that gives the least amount of kinetic energy that, if applied, can get you to a point where you don't have any potential energy stored with the planet anymore, that you're so far away there's no energy stored. In summary, to find the escape velocity, we're going to set gravitational potential energy. We're going to imagine a mechanical energy of 0, and we're going to figure out the relationship between kinetic and potential energy that would make that happen. So we're going to assume that this object begins on the planet's surface for our derivation, and we're going to use big M for the planet. We will use little m for the object in question, and we're going to use big R for the planet's radius, because that is the starting location of the object, and also it's an important dimension in energy. Okay, so we're going to set mechanical energy equal to 0, and mechanical energy is kinetic plus, in this situation, gravitational. All right, so these two values are going to add up to 0. Well, kinetic energy is 1/2 mv squared, and then gravitational potential energy is negative g big M little m over r, and that is going to equal 0. Okay. So they add up to 0. The amount of kinetic plus the amount of gravitational is going to equal 0. And I can move gravitational over to the other side. I get 1/2 little m v squared equals g big M little m over r. And so the first thing that you see that you might want to do is cancel m. As we saw a lot when we studied gravity, the mass of the little object can cancel, or the object of our acceleration problem or whatnot. And then if I solve this for v, right, I have 1/2 v squared equals gm over r. So v squared is going to be 2gm over r. So if I multiply both sides by 2, and then if I take the square roots, I get my equation. So v escape equals the square root of 2gm over r. Okay, so what does that mean? That means that the escape velocity depends on the planet. Sorry, it depends on the dimensions of the planet, so the radius of the planet, as well as the mass of the planet. So the heavier the planet, the greater the escape velocity. On the other hand, the larger the planet, the smaller the escape velocity, implying that there's like less density to that object. And so this is the equation we're going to use. This is not on the equation sheet. There are plenty of questions that I've seen about escape velocity in the new pile of questions from the College Board. So it's one that you have to know how to get, and or memorize it. I can see this being like a derivation problem, but also like a set of multiple choice questions about escape velocity. Now, to put this into perspective or some realism here, if this object were on Earth, this would be how you would calculate its escape velocity. So 2 times the gravitational constant times the mass of Earth, so about 6 times 10 to the 24th kilograms, divided by the radius of the Earth, about 6.4 times 10 to the 6 meters. So it's like 63,000 kilometers, or 6,300 kilometers, and then the square root of that. So if we find the escape velocity of an object relative to Earth, we get 11,000 meters per second, or about 11 kilometers per second. Now, that's pretty fast, right? To put that in perspective, the International Space Station has a speed of about 7.5 kilometers per second. So it's going really fast, but it's not fast enough to leave the orbit of Earth and escape. If you go out to the moon, the velocity of the moon is a little bit over 1 kilometer per second. Now, we studied circular orbits a little bit already, and the way circular orbits work is the further away from the planet you are, the less speed you need to keep that orbit. So the International Space Station is going incredibly fast. The moon is still going very fast, but not nearly as fast as ISS. And that's escape velocity.